In this video, we want to look at the principle of conservation of mass. Now, during a chemical reaction, the total mass of the substances involved remain constant. Now, what it means is that the mass at the beginning is the same as the mass at the end. So, for example, if we take a generic reaction, say we react A with B to produce C and B, what it means is that if we add the masses of A and B, it should be equal to the masses of C and D. So, for example, if the sum of the masses of A and B is 2, then the sum of the masses of the product, i.e. C and D, should also remain the same. So, in brief, the principle of conservation of mass says that the masses at the start of any reactant, or the masses of the reactants, should always be equal to the masses of the product. So here, if we react copper sulfate with sodium hydroxide, the product we're going to have will be copper hydroxide and sodium sulfate. The masses of copper sulfate and sodium hydroxide should be equal to the sum of the masses of the product, which is the copper hydroxide and that of sodium sulfate. Okay, so why doesn't the masses change in any chemical reaction? The masses do not change because in chemical reactions, no atoms are made or destroyed. Now, it means that the reaction just changes how the atoms are bonded together. In any chemical reactions, the atoms are not destroyed or created. No new atoms are created nor destroyed. So the masses remain the same. Now, what really happened in the reaction is that there is just a rearrangement of the atoms in bonding. So if we take these two guys here, let's say they are our reactants, and we react them together, we're going to have the same guys in the product. The only difference is that they have been arranged differently from where they were. Now, so here, let's say they are talking together, they are free, they are not holding hands. In the product, they are holding hands. It's the same guys, but they are holding hands. The bonding has been changed in the product. So that's what happened in chemical reactions. We do not create new atoms, and we also do not destroy the old atoms. Okay, so the whole principle is that the principle of conservation of mass says that no atoms are destroyed or created in a chemical reaction. The total mass of reactants at the start of a reaction is equal to the total mass of the product at the end, and this is called the principle of conservation of mass. Okay, like I said before, the sum of the reactant masses should be equal to the sum of the product mass. If there is any change or any loss, that means that something might have gone wrong. According to the principle of conservation of masses, the masses of both the reactants and the product should be the same. Now, with that in mind, let's look at limiting reactants in any chemical reaction. Now, the amount of product formed in a reaction will depend on the limiting reactant. This is the reactant that runs out first, bringing the reaction to an end. Now, in any chemical reaction, let's take here again back to our generic reaction. If we react A with B to give us C and D, let's say we have 5 grams of A and only 2 grams of B. As the reaction proceeds, at some point all the B reactants will finish. Now, once that is finished, the reaction cannot proceed to come to an end because there is no more B to react with C to produce, to react with A to produce C and D. And so without B, the reaction comes to an end. And that element or the substance that finishes first is what we call the limiting reactant. And The other reactants are said to be in excess because when the reaction finishes, there will be some of the excess left. The excess reactant will remain, the limited reactant will finish, whereas there will be some of the excess reactant remaining. Now, this table on the right here shows hydrogen gas production during a reaction between a small amount of magnesium and excess dilute hydrochloric acid. If we react dilute hydrochloric acid with magnesium, we're going to have hydrogen produced. Now, after how many seconds was all the magnesium used up? So in this particular reaction, magnesium was the limiting reactant. What it means is that it got finished at some point. Now we want to use this table to identify the time at which all the magnesium was finished. Now, so if you look at the table, you will see that the time at which the magnesium completely ran out was when it was after 270 seconds. Now you see that after 270 seconds, when you go to 300 seconds, the amount of hydrogen produced remained the same. Now what it meant is that there was no more magnesium to react to produce additional hydrogen gas. So limiting reactants are the reactants that runs out, and the excess reactants are the reactants that remain after the reaction. Now, how do we demonstrate conservation of mass? Now, you can be given an equation asked to demonstrate that mass has been conserved in that particular reaction. Now, how do you do that? We can use relative formula masses with simple equations to show that mass is conserved during a reaction. The RFM, or the relative formula mass of a compound, is the total of the relative atomic masses of all the atoms in its formula masses. We've already gone through this, how to work out the relative formula masses. You do that by summing up all the individual relative atomic masses. Now, how do you show that mass has been conserved in a particular reaction? Now, you can do that by working out the relative formula masses on the left side and comparing it to the relative formula mass on the right, i.e., you calculate the relative formula mass of the reactants and compare it to the relative formula mass of the product. If they are the same, then mass is conserved. So if you get any question where you are asked to prove that mass has been conserved, calculate the relative formula mass of the masses of the reactants and compare it to the relative formula masses of the product. If they are the same, then mass has been conserved. So let's look at this particular example. We got sodium reacting with oxygen to give us sodium oxide. Now, first of all, we have to calculate the relative formula masses on the left side, and so we will need the relative atomic masses. The relative atomic mass of sodium is 23, and that of and so we have 4 lots of sodium, multiply it by 23, you get 94. Go to oxygen. The relative atomic mass of oxygen is 16. We got 2 lots of oxygen in the oxygen molecule. Multiply 2 by 16, you get 32. The next thing to do is to add the relative formula masses of the reactants, which is 92 plus 32, and that should give us 124. Let's go to the product side. The product side is the sodium oxide. We have 2 lots of sodium and 1 lot of oxygen, and all of them, we have 2 lots of the compound here. So if you add them up and multiply by 2, you're going to have 124. Now you can see that the total relative formula mass on both sides of the equation are the same. So no mass has been lost. No mass has been lost means that mass has been conserved. Now, what are the rules for reacting masses? we are sometimes required to also calculate the masses required in any particular reaction. Say, as a chemist, you go into a lab, you want to make specific amount of a compound. Now, you want to find out how much of the reactants you need in order to get specific amount of the product. Occasionally, you might also be required to calculate how much of the product you will be made if you have specific amount of the reactants. So let's look at the rules that govern such calculations. The first step is to write down the balance symbol equation, and then go ahead in the second step to write down the relative atomic or the relative formula masses of the reactants and the product. Next step, use the balance equation to write down the ratios of reactants and product, and then convert to ratio of the reactants, and then calculate the scale factor and apply this to the ratio of the reactant masses. These are the steps that you have to go through. Let's look at the specific example, and let's look at the examples here. Here you have the mass of an ion reacting with a copper sulfate solution. What mass of copper will be made? Now, so you are required to calculate the amount of product that will be made if you have specific amount of a reactant. Okay, so the step one, let's go through our steps. Step one, write down the balance symbol equation. So here you will need to apply your balancing of equation skills. Here you know that you are reacting an iron with copper sulfate, and you know that one of the product is copper. You must know the other product and write the balance equation down. And so this is what our balance equation will look like. Okay, and the next step is to write down the relative atomic or formula masses of the element you are looking for. Now, in the question, the only element we are concerned with are iron and copper, because the question says that if 28 grams of iron react with copper sulfate solution, what mass of copper? So we are looking for copper if we have specific amount of iron. So these two elements are our concern. We don't really care about iron sulfate at this stage and copper sulfate. So let's go ahead, write down the relative formula masses. So we have the relative formula mass of iron is 56, and the relative formula mass of copper is 66. Step 3, write down the ratio of reactants and products. Let's go to our equation. What is the ratio of the reactant to the product? We have 1 mole of iron and 1 mole of copper. The ratio is 1:1. So let's put that down. Fe is to Cu is equals to 1:1. Step 4, convert the ratio of the reactant masses. Now, so let's, instead of the ratio, we put the reactant masses there. 1:1. The relative formula mass or the relative atomic mass of iron is 56. So it will be 56:46. 56:64. Okay. Step 5, calculate the scale factor. In other words, divide the mass that's been given by the relative formula mass. In simpler terms, work out the number of moles. Work out the number of moles of the iron, the one you know the mass, and that will be 28 divided by 56. That should give you 0.5. And the next step, multiply the number of moles by the relative formula mass of the copper to get the amount of copper that you will be made. So you take the 0.5, multiply by 64, and that should give you 32 grams. So if 28 grams of iron react with copper, 32 grams of copper will be produced. If 28 grams of copper sulfate 28 grams of iron react with copper sulfate solution, 32 grams of copper will be produced. Now the steps again, write down the symbol, the balance symbol equation. You then go ahead and write down the relative atomic masses. Look at the ratio, 1:1, write that down. Then write the reacting masses down as a ratio, and then calculate the number of moles of the iron, which is number of moles we know is mass over molar mass, and the molar mass of iron is 56. The mass that has been given is 28, so divide that, you get the number of moles. Because the ratio is 1:1, it means that the number of moles of copper is also 0.5. Then we know that mass equals to number of moles times relative formula mass. We know the number of moles of copper is 0.5, multiplied by the relative formula mass of copper, which is 64, and that should give you the mass of copper that will be produced. Let's look at an example here. How many grams of calcium oxide will be produced by the thermal decomposition of magnesium carbonate? So if magnesium undergo decomposition, we want to find out how many grams of copper oxide will be produced. We've been given the balance equation here, and the ratio of calcium carbonate to calcium oxide is 1:1. Okay, is 1:1. So let's go ahead and see. So here we got our balance equation. The ratio of calcium carbonate to calcium oxide is 1:1. Okay, let's go ahead and put the relative formula masses in. So here the relative formula mass of calcium carbonate will be 40, which is the relative atomic mass of calcium. Add that to 12, that of carbon, and then you have 16 times 3. That should give you 100. Now, this is to calcium oxide. Calcium oxide is 40. Add that to the relative atomic mass of oxygen, which is 16, and that should give you 56. We've already done that in the previous. And so 100:56. Calculate the number of moles of calcium carbonate, and that is mass, the mass that have been given, which is 100. Divide that by 100. This should give you 1. So the number of moles of calcium carbonate is 1, and the mole ratio is 1. So the number of moles of calcium oxide is also 1. Now, what mass will you get? Mass equals the number of moles over relative molar mass. What is the relative molar mass of calcium oxide? We've already worked out to be 16. So multiply that by 1, and that should give you 56. And so the answer is this 56. Okay. Let's look at more examples here. If you have 48 grams of magnesium, what mass of oxygen will react with this? So here you've got 2 reactants, magnesium and oxygen. Now, as a chemist, you have 48 grams of the magnesium, and you want to find out how much of the oxygen you need in order to get specific amount of magnesium oxide. Okay, now so let's go through our steps. The balance equation has been given us. You must be able to write balance equation at this stage. It will not always be given to you. You have to be able to write your equation, know your reactants and your product, and balance the equations. And so that has been done. The balance equation shows that the ratio of magnesium to oxygen is 2:1. The relative atomic masses of magnesium is 24, and that of oxygen is 32. Now, if you combine these two information of the reactant masses, we're going to have magnesium is to oxygen will be 2 lots of the magnesium, which is here, times the 24 is to 1 lot of oxygen times oxygen molecule, the 32, which is the relative formula mass of oxygen molecule, and that should give you as 42 grams is to 32 grams. Now, what that means is that if you have 48 grams of magnesium, you will need 32 grams of oxygen to react with. Okay, so go through the steps, write your balance equation, write the ratios, and then go ahead and write your relative atomic masses and convert that into the ratio and go on to work out the mass that is required. Okay, so we have our 2 moles of oxygen, magnesium reacting with 1 mole of oxygen. You can also use mole ratios. You can calculate the number of moles of magnesium in this reaction and then multiply by 2 because divide by 2 because 2 lots of magnesium reacted with 1 mole of oxygen. So the number of moles, again, we need number of moles equals to mass over molar mass. Divide the mass of magnesium that has been given in the question by the relative atomic mass of magnesium, you get the number of moles of magnesium in this reaction. And since the ratio is 2:1, once you get the number of moles of magnesium reacting with oxygen, if you want the number of moles of oxygen, you divide by 2 because 2 lots of magnesium is reacting 1 mole of oxygen. So you divide by 2, that will give you the number of moles of oxygen. Once you get the number of moles of oxygen, multiply that by the relative formula mass of oxygen to get the amount of oxygen that will react with 48 grams of magnesium. So here, if you divide the mass of magnesium, which is 48, by the relative formula mass or the relative atomic mass of magnesium, 24, you get 2. Okay, so the number of moles of magnesium in this reaction is 2. Therefore, the number of moles of oxygen reacting in this reaction will be 1. Now that we know the number of moles of oxygen is 1, we can go ahead and calculate the mass of oxygen that we require. And mass from our formula is number of moles times relative molar mass. And the number of moles is 1 multiplied by the relative molar mass of oxygen, which is 32. We're going to have 32 grams. 8 grams of magnesium. What mass of magnesium oxide will be produced? So here we've been given the amount of magnesium reacting and we want to find out how much of the product will be produced. So follow the same MOD. The balance equation has been given already. You should learn how to write your balance equation. In this case, it has been given to us. So we can go ahead and look at the ratio. The ratio of the magnesium to magnesium oxide is 2:2. Now, the next step is the relative atomic mass of magnesium, which is 24, and the relative formula mass of magnesium oxide will be 40. Now, if we combine these two information, the ratio of the reacting masses will be magnesium is to magnesium. And so we're going to have 2 multiply the ratio by the relative atomic mass is to the ratio times the relative formula mass, and that should be 48:80 grams. So 48 grams of magnesium will produce 80 grams of magnesium oxide. Okay, follow the same. In other words, you can calculate the number of moles of magnesium and use that to find the number of moles of magnesium oxide in this reaction. Now, the number of moles is mass over molar mass. Get that. Multiply the number of moles of magnesium oxide by the relative formula mass of magnesium, and that will give you the amount of magnesium that will be produced in this reaction. Let's look at another example here. Here, if you have 48 grams of magnesium, what mass of magnesium oxide will be produced? If you have 480 grams of magnesium, what mass of magnesium oxide will be produced? In the previous example, we were given 48 grams of magnesium, and we worked that out to get 80 grams of magnesium oxide. What this means is that if you have 48 grams of magnesium, you will get 80 grams of magnesium oxide. Therefore, in this question, we've been given 480 grams of magnesium. What mass of magnesium oxide will be produced? Now, I can use proportionality to do it. You can go through the same steps. So here you got your equation here, balanced equation, and the ratio is 2:2. And the only thing you are doing here, you are going to have magnesium is to magnesium oxide. It's going to be 2 times 24 is to 2 times 40 in the previous example when we were given 48. Now, here we are using 480 grams of magnesium. So the scale factor will be 480 divided by 48, and that should give you 10. And so you use that one to work that ratio, multiply that by the previous example to get 800. Right. So if we use the previous example, in that example, 48 grams of magnesium gave us 80 grams of magnesium oxide. If 48 is giving us 80, what would 480 give us? Now, if we go back to our mass, if more, less divide, if less, more divide, we're going to have 480 divided by 48 times 80. And what are we going to get? 800 grams. Use proportionality. It's similar to the previous example or the previous question. In that question, 48 grams of magnesium gave us 80 grams of what? Magnesium oxide. Therefore, what will 480 grams of magnesium give us? If more, less divide. So 480, the more we divide by the less and multiply by the 80, and that should give us what? 800 grams.